the LHC, and I have nearby me Michael Dozer, who is going to give tonight's presentation. Michael, thank you for accepting to answer a few questions just before starting this conference, which is actually in French and can be followed on a podcast entirely for the hour it's going to be, but in French. Obviously, to my mind, and I think to anybody who doesn't know too much about physics, is why on earth building such a weird piece of machinery like the LHC underground here on the planet when you want to look after mysteries that are out there in the universe?
Well, there are two reasons. First of all, it's much cheaper to build here, and although the LHC is very expensive, it's in fact cheaper to build something like that here locally, where you can actually bring in materials. But the real reason is that the physics that you're looking at is physics that are very much at the beginning of the universe. If you look out into the universe with a telescope, you can see very far back in history towards the Big Bang. You can look back almost to 500 million years with how the universe is built. You cannot see anything beyond that because light didn't make it out after that, earlier than that.
So that is 300,000.
That's 300,000 years after the Big Bang. So if you want to see anything that happened earlier than that, well, either you have to detect gravitational waves or neutrinos from much earlier times, which is currently impossible. We don't know how to do that. These very, very weak signals.
They're still trying, though.
But these are much, much weaker signals than what people are trying to look for right now. So this is maybe a few centuries in the future in terms of what our technology will be able to do at that point. But if you really want to find out what's going on in the universe at the first instance, what you have to do is simulate it in a lab by colliding particles, which is basically what happened in the first instance of the universe.
So basically recreating a universe in miniature.
Recreating some aspect of the first few moments. Not a whole universe, a little bit less ambitious than that, but just what happened in the first few.
Okay, that's clear. And now, how come that this machine has to go at the speed of light, has to push particles at the speed of light, has to be 27 kilometers around, and has to have super ultra vacuum inside? What determines this characteristics that you chose?
Okay, so the one thing that determines the whole thing is really the fact that you have one equation, E equal mc squared, which says that if you want to produce something massive, you have to put lots of energy in it. If you have a collision between two particles, and they're moving very fast, you can generate as much energy by having them collide, by transforming their kinetic energy into the mass, but that means they have to have very high kinetic energy. Very high kinetic energy means moving very fast and using heavy projectiles. If you shoot two mosquitoes at each other, it's not the same thing as shooting two cannonballs at each other. So ideally, you want something very heavy, like a proton, rather than something light, like an electron, and you want to move it as fast as possible. So you can accelerate a particle by giving it a lot of push, with electric push, but the important thing is that it has to go around an accelerator, otherwise you have to build a very large number of accelerating devices, which is very costly. So rather than building many, you build a few, but you keep using them again and again and again, which is what the LHC does. Any big accelerator does that. The problem that you have then is that these very heavy particles don't want to go on a curve, they want to go straight. So you need a very strong magnetic field to bend them, to keep them on track. So ideally, you build a very big accelerator. The bigger the accelerator at a certain magnetic field, the more energy you can put into the particle and still keep them inside the accelerator. And so basically the LHC has made the choice of using the highest possible magnetic field you can build, which is about 8 Tesla, and using the biggest accelerating device that you can build, the biggest tunnel, which is the old left tunnel. And that sets the scale right away for the energy spread of the LHC, which, luckily, is in an area where the physics really gets interesting.
So you already had a tunnel that is 27 kilometers around. What if you had to build it from scratch? Would it still be 27 kilometers or even bigger?
Basically a compromise between how much energy you want to put into the particles and how much money you want to spend. Making it any bigger, making a bigger tunnel would make it that much more expensive because you need the civil engineering and you need to use more magnets. You need to build more magnets. You need more electricity. You need more cooling. It gets very expensive very quickly.
Okay.
So in a way, the LHC is an ideal compounder atom problem. They've discovered that atoms are basically a nucleus with a shell of electrons around them. They've looked inside the nucleus. They found that that's protons and neutrons. They looked inside that. They found that protons and neutrons have substructure, which is quarks. And they've discovered that all these particles that you can think of producing are in fact just made of a very small number, a simple set of 6 quarks and 6 leptons, and that the forces with which these particles interact are also very small numbers. There are only 4 forces that exist in nature. So in a way, that's the outcome of 100 years of research in particle physics in 5 seconds. And the same development has taken place in cosmology and in astrophysics, where people have gone from looking at stars in our solar system, in our galaxy, to looking at other galaxies, to looking very far back into the past, to seeing the galaxy and seeing the primordial radiation of the microwave, which is the temperature distribution of the universe when it was only 300,000 years old. And these two mesh very nicely together in a way that is somewhat surprising. It's very gratifying in a way that the two fit together and that we have a model that explains pretty much everything you can think of observing. So in a way, there's no mystery there. Now, where the mystery happens is that many of the things that our models explain rely on other things. For example, the fact that our quark model, our standard model of particle physics, predicts that all the particles are massless. We have no reason why they should have mass. You have to come up with a good explanation.
But they do have mass in it.
Obviously, yes. So the model is wrong somewhere, and we have to find out what's wrong with the model, and to see if we can patch the model. And there is a patch called the Higgs particle, which people are very hopeful in finding. But there are other mysteries. For example, if you look at the universe, we only can see the stars of the other galaxies. But if you really look at what's in the universe, you see that there's a whole amount of matter that you cannot see. It's just not bright. It's not shining. There's no light produced by it. It's dark matter. And there's about 6 times more of this dark matter than the matter.
Thank you.
C'est toutes les étoiles, toutes les galaxies, tout ce qui est visible dans l'univers. La matière sombre correspond à 5 fois plus de ce que nous connaissons que ce que nous voyons actuellement. Et là, nous ne savons pas ce que c'est. Nous ne le voyons pas. Nous ne pouvons que le voir indirectement par ces effets gravitationnels. Et je vais mentionner tout à l'heure, expliquer tout à l'heure que le LHC peut trouver peut-être un candidat pour cette matière sombre. Et là, c'est une catastrophe. 75% de l'univers sont inconnus. Et là, il n'y a même pas de candidat pour expliquer ce système. Donc, le domaine d'application de notre modèle, dont nous sommes si fiers, qui explique tout, c'est ce petit bout de rien. Donc, un peu d'humilité. Alors, dans ce contexte-là, on peut se demander que peut apporter le LHC. Et ces 3 domaines sont les domaines où le LHC devrait pouvoir apporter le plus. L'origine de la masse, expliquer pourquoi des particules ont de la masse, et ça, c'est par interaction avec le champ de Higgs et donc la découverte de la particule de Higgs, que je vais expliquer juste après. Éventuellement, des particules supersymétriques pour expliquer ce qu'est la matière sombre, et puis finalement la possibilité de découvrir des dimensions supplémentaires à travers la théorie des cordes, qui sont prédites par la théorie des cordes.
And right after the conference, we're here with some of the members of the audience.
I'm a secretary for bank in Geneva.
Okay. Did you know or did you suspect that what we know about our universe is only 4% of what exists?
No, I really had no idea about that. It was really interesting, but I didn't know.
And Jeremy, you work at CERN in the passive sector, but only for a month. You just arrived.
Yes, I just arrived and I'm doing a placement for my studies.
So you're finishing your studies?
Yes, but I also want to continue after that to learn more and to study more.
Yeah, and did you know about the Higgs boson? This phantomatic particle that they're looking for with the LHC?
I've heard some information about it, but already I didn't know what was this particle.
And now are you curious to find about it?
Yes, a little more, of course, but it's still a little dark for me.
A little bit dark for you.
Yes.
Let's hope the LHC will clarify that.
Yes.
And you?
CERN is so close to us, and having such a big
Surely,
search
for
center
people working in
available.
computing, the home of the web is definitely something
That's right.
fascinating.
That's right.
But were you also curious about the mysteries of particle physics?
Right, I am in cosmology, but really as an amateur.
What did you like most about the presentation today?
Just making me feel what the LHC is for. So I had no idea. I knew it was for particle and detection and experiments, but I didn't know which one. And I think it was brilliantly explained.
Today?
Yeah.
Thank you very much.
Thanks.
last December, and he gave the LHC 5% chances to find a black hole.
He's a hopeless optimist.
What's your bet for the Higgs boson?
Oh, for the Higgs boson, I'd be willing to bet my usual crate of champagne. If somebody will bet against the crate of champagne, another crate of champagne, at least even odds.
Okay, then we'll see in a few months.
Find somebody who will take the bet.
I take it.
Okay. So no Higgs?
At the LHC.
Okay.
Something else.
Very good. Very good.